Yeah, welcome to Learning SuperPro for Bioengineers, example 1. This time we talk about economics. Yeah, last time we have set up a simple process with SuperPro 1. In this example 1, we have set up a neutralization process. This time we want to make money out of this process. Of course, it's hard if you produce sodium acetate with such a process to get rich, but at least we will try. Okay, so what do we want to do? We assume now that sodium acetate is our product. Yeah, you still have the example which is linked down there on your hand, and the sodium acetate is the product which came out of our process, and we want to assume now that this is subsequently sold. We don't do any other downstream treatments or so. We sell it like it is. The people will buy it, believe me. You just need the marketing which tells the people that you should buy it. Okay. We assume that we can purchase the raw materials for $10 per kilogram and sell our sodium acetate for $11 per kilogram. And now let's see how we have to adjust everything in order that this works. So let's go right away to the software. You remember, we have our neutralization process. We have pumped in acetic acid 20%, sodium carbonate 15%, and then we let it react. We have termed it a neutralization process. Now, of course, we just want to produce with this process, and this is what we became out, and this is now our product. Now let's make money of our product. That's the intention now. Okay, how can we do that? So first of all, we need to tell the software where does the money come out, and we need to tell the software what are the costs. So how we do that? First of all, we need to classify the stream. So the software wants to know what stream is a waste stream, what stream is a revenue stream, what is a raw material stream, and we need to assign that in the software. Yeah, so this is how we have classified our stream. Last time we just changed, I wanted to change this, edit labels to adds product stream. Okay. And now we want to classify the stream. So we need to assign to the software which stream is our product stream, which stream is our raw material stream, which stream is our waste stream. So here we go. So we go simply to tasks, stream classification, and you see here now we have a window where we can classify a different stream. We can classify the output streams, input stream, and we can say what is our main product revenue stream. So let's start with the output streams. Now, this is our NaCl product stream. You see, if you put the stream name in clear letters and it's just not the S104, you know what it is, and then it's less likely that you make errors here. So let's classify this as an revenue stream. Now, our input streams are automatically already classified as raw materials. You could change that, but this is, of course, already correct. Now, what you should not forget is we need also to classify here our stream NaH, sodium acetate, as our main product stream, and the calculation of the revenue should be based on a single component in the stream, namely on sodium acetate. So if there are other components inside, that doesn't matter, because if you if you produce 1,000 kilograms of your stream, the revenue is not in the 1,000 kilograms with the water, it's in your sodium acetate. So therefore you do it. It can be different, it depends on what your process is. So, and now, okay, we're happy at that. So we don't see a change, we just have classified the streams. Now, of course, we need to assign the costs somewhere. And where can we do that? Well, the costs are associated with the chemicals. So we go to the substances, very simple. We go to tasks, pure components, register, edit, view properties. Here we are, we already know this window. And now we start with acetic acid. And acetic acid, as you double click, as you remember, acetic acid is our raw material, and we said that the raw materials cost you $10 per kilogram. So we go to the economics tab here, And we change the purchasing price to $10 per kilogram. You see that the purchasing price, which is already included here, is a more reasonable price, but we say, unfortunately, we can only buy it for $10. Selling price, wastewater disposal price, we keep untouched. Okay. Now we go to sodium carbonate, which is also a raw product. We do the same. It's $10. And the selling price, we keep untouched. Okay. And finally, we come to our sodium acetate. And sodium acetate is our product. So therefore, we earn money with that. Purchasing price, we don't care because we don't purchase it. We just produce it. And our selling price now is $11 per kilogram. Okay. So that's it. Everything is fine. And we have defined now our prices. What comes next? Well, now we can do the economics analysis. We have assigned the streams. The software knows what stream is doing what. So we simply do the mass balance. And we do now the economic balance. So we perform the economic calculation. And then we just go to View and look at the executive summary. And here we are. So this is now the executive summary for this project. So you see, we have our investment costs. We have the investment charged to this project. There is only this project. So of course, everything is charged to this process. And we have the annual operation costs, which are high, and the annual revenues, which are unfortunately lower than the annual operation costs. This makes us a bit nervous. This means already that it's unlikely that we make a lot of money with this process, already looking at these values here. Now, if we go down here, we see that our gross margin is negative and our net present value is really negative. In other words, if we invest in such a process, we will lose money. We will lose a lot of money. So nobody will go for this process. So therefore, of course, your job is, if you start like this, your career is gone. So, but if you decided, I want to build up a company producing sodium acetate, don't get shocked at that point. Go further. You just need to find someone who gives you the money. You remember there are presidents getting money for real estate projects also. So why shouldn't you get the money? So here we go. So, but what did you need to do? First of all, go to your marketing department and ask them whether you could achieve a higher sales price. Your marketing department tells you no. Then you go to your finance department whether you can buy the raw material for a cheaper price. Also no. So your administration is of no use. So what you have to do is you have to go down with your operation costs. Yeah, and you watch TV. What's the best way to reduce the operation cost? Reduce the labor. Instead of putting 5 people around, sack half of the employees and then everything is fine. Usually this works on short term maybe well, but on long term it's not a good idea. But nevertheless, I showed you now in the software how you can do it. And in software, it's so easy to click around and reduce the costs. So therefore, management often decides based on this, which is maybe not very sustainable. But we said, okay, with this calculation, for sure, we don't need to ask someone give us money, because it makes no sense. You will just lose money. So the question is, how can we make this process profitable? Well, I said one thing is labor cost. This is the main thing usually what you can change, as we cannot change the price for the raw materials and we cannot change the selling price. Now, so how can we change that, and where can we find these labor costs? Well, they will not be at the vessel, because if the vessel stands around, there is no labor. They will be in the operation. So we have to look in the operations whether we find a possibility to change the selling price there. So here we go. So we right-click on our neutralization procedure, and now we go simply to the first operation, which is the charge operation. And if you have a look now at this charge operation, you see these different tabs, and we have already worked with the operation conditions. We have worked with event emission tab, but you see there is also a labor tab. So let's click on the labor tab, and you see this makes us happy because here we see we have our operator, and you see that we have the operator is charged 2 labor hours per hour is charged on this process. Well, how can one operator work 2 hours per hour? This is of course not possible. This means that we have 2 people fully charged, fully placed on this charge process. If you do a GMP production, this is the case. So if you weigh something in, this is very critical. So if you produce a pharmaceutical, for example, then this will be like it is. However, we say, well, we have purchased our sodium acetate as a sodium carbonate as a 15% solution. So we just, the operator just needs to put in a pipe in this and pumps it in. So you can do that way more quickly. So the pumping takes time, but he doesn't stay there for a while. He puts that in, programs it, and then everything goes on. So we say instead of 2 hours per hour, we can do that in 0.25 hours per hour. It's 0.25 hours per hour means for 1 hour charging, this operator needs 15 minutes. And for the remaining time, he can do something else. So of course, this only works if you have a company with other projects going on. Otherwise, he will just do nothing, but still you pay him, of course, still. So therefore, if you have a small company, these things will not really turn out. But if this is typically how it's done in industry, that you charge labor to a project as long as the people work on that project and they write their hours on the project. And if they work on another project, the labor is charged then to the other project. This is how you do cost calculations. This is what you have learned in business administration. Yeah. Okay. So now we have this part. So now let's go to the other tab. So what we do is we go directly to the next operation. Same tab is if applicable. Yes, we have also for the second charge operation, we have the same. So also here we put only a quarter labor. Now we go to the next, and you see also in the for our reaction, we have this, and you see in the reaction, we have just 1 worker, so it's less, but still we say, why should this operator stand around and watch the reaction in the vessel going on? There is nothing he can do. He can just, if there is an alarm or so, doing something. But of course, we have an operator having large monitors, and he supervises 10 processes at the same time. So instead of charging it, so in this case, as he can supervise 10 processes at the same time, it's of course just 0.1. And finally, the transfer out process, it's just pushing a button. Also here, it's not 2 hours, it's 0.25 hours. Okay. So now we have changed. We have just reduced the labor quite a bit. And now let's look what's happening. So we do the mass balance again. We do the economic calculation again. And again, let's view the executive summary. And bam! Look at this. Our net present value is really positive. This is the best process ever. We should now invest in producing sodium acetate. You can show this to and try to get money from an investor who has no idea from the chemical industry. Sometimes that works. That's always a good idea to try. However, I can tell you before you start, that might be risky, because I said if it's your only process, it doesn't help you because the people are still there. So you cannot just charge them on this project if there is no other project ongoing. That's one point. The other point is what you see, the investment costs for such a project are quite high. And you say, well, they are too high. It's just one reaction vessel. But this reaction vessel, of course, is not just a vessel, but you have all this control equipment around, you have cooling and so on. So this makes this equipment already expensive in a size of 2 meter cubes. And it's not just the vessel. The software also calculates in all the tubing and so on, installation installation you require. So therefore also these costs are quite reasonable. I would not fiddle around too much there if you cannot argue why in your case it's cheaper. So that's about how to make this process profitable. Again, you have learned now the best thing is to sack the people and then everything is fine. Yes, this is how business administration works, by the way. We produce now at present sodium acetate. Now, this is not really making sense. Nobody will produce sodium acetate with such a process, buying acetic acids and buying sodium carbonate and then producing sodium acetate. It's quite the profit will not be great in this case. Second, the point is it's more likely that you have an acidic outflow, for example, a waste stream, and your problem is that you need to neutralize it before you release it to a wastewater treatment plant. In this case, of course, it's not a revenue stream. In this case, it's a waste stream, and in this case, it's cost. And usually, a wastewater treatment plant charges you with respect to, for example, chemical oxygen demand. If you're industry, it's not like if you're a private household. A private household pays whatever 2 euros or 3 euros per meter cube wastewater. And industry is charged for the volume and for the content. So if you make wastewater in the industry, you're charged for what is actually in your wastewater. One parameter will be the chemical oxygen demand. So in other words, how much carbon is there? Because that's what your wastewater treatment plant does. It oxidizes that, and they need to adjust the chemical oxygen demand, what is going in order that they don't overload their wastewater treatment plant. And the other thing is there might be some toxic substances or so which are charged extra, and they require you to have a certain pH. Now, let's assume here our wastewater, we are charged for the chemical oxygen demand and we are charged for acetic acid. Yeah, let's say because it's acidic or because it's somehow toxic. Yeah, so for this reason, before we release it, we need to neutralize the acetic acid. Again, we do it just partially. We do this with sodium acetate as we did before. So we use our first process, not the optimized process, our first process where we have 1000 kilograms of acetic acid, 20%, which is our waste stream coming out from our factory for whatever reason, and we neutralize it with 1000 kilogram of sodium carbonate, 15%. So we partially neutralize it. Now we want to know what comes out is, of course, then a lower amount of acetic acid, and this is priced, and the chemical oxygen demand is priced. And let's assume now, based on what is written in the example, the wastewater treatment plant charges now $11 per kilogram acetic acid. So they take samples and measure it. And in addition, they charge $5 per kilogram chemical oxygen demand. Yeah, so we need to neutralize at least partially. And we take this with our first attempt. By the way, of course, this setting we have here, there is another possibility in the software to use this neutralization approach. Usually you have then a pull operation, which just pulls the sodium acetate you need to neutralize. So you would not implement that like this. This is just now a demonstration how you can implement waste streams and costs. Okay, so then, of course, we have to reclassify our stream. They have been classified now as revenues. Now they're waste. So we go again to tasks, stream classification. But now, as I said, it's no more a revenue stream. My sodium acetate is a aqueous waste stream. Automatically, this here now gets kicked out. So the acetic acid and the sodium carbonate, of course, is no more a raw material. We just put it as none. And then everything is fine. It's not a revenue stream anymore. Okay. No main product stream has been defined. Proceed. Yes. So, of course, as you want to make money, usually with your process, this now makes no sense. The software is asking you what's going on because you can't make money. You will only make costs. But now we want to optimize the cost. That's okay. Yeah. So we know what we do. We tell the software. Okay, now we need to put in the costs. So of course, obviously, we do the same as before. It's within the substances. The COD demand comes, of course, not from the water. It comes from the organic load. So the organic load is simply our acetic acid. It's the sodium carbonate. The organic load is 0. You cannot oxidize there something. But of course, the sodium acetate, it's the same organic load in principle with like the acetic acid. So we need to put the COD value there, and we need to use the COD value in order to calculate then the costs. So here we go. We go to tasks, view components, again, register edit view properties. And now let's start with acetic acid. Okay, so we first go to economics. Now we have no more a purchasing price. This is 0. But we have a waste treatment or disposal cost price. Now for acetic acid, it is given that it's $11 per kilogram. So we are charged $11 per kilogram for the waste disposal. Now, then we go to the tab Aqueous. Yeah? So we have here different categories. We go now to the tab Aqueous. And here you see that we have a COD. We have a chemical oxygen demand. We also have a biological oxygen demand, a ratio, but we say we charge for the chemical oxygen demand. The remaining part is not interesting for us. So you see here a value is there. It's 1.066 roundabout. And this is the chemical oxygen demand of acetic acid. This means if we release 1 gram acetic acid, we have a chemical oxygen demand of $1.06 1.06 grams, and we're charged, as you remember, $5 per kilogram COD. Yeah. So now we need to calculate this value. If you release 1 kilogram, how much does 1 kilogram cost? And you see 1 kilogram of acetic acid has a chemical oxygen demand of 1.065 kilogram oxygen. And of course, 5 kilograms and this we simply need to multiply then with the $5. So this we take just the pocket calculator. And so now we just use the calculator and we just calculate. So we have 1 kilogram is 1.0657 kilograms COD. So we just multiply then I have a German notion here, so the comma is the point, fold, and the price is $5 per kilogram. I should then also take the fold now, $5 per kilogram. So this means we are charged with respect to the chemical oxygen demand $5.33. Yeah. So we need to add this now to the cost of the acetic acid. So a release of acetic acid costs us $11 because we have the acetic acid inside. And in addition, $5.33 due to the chemical oxygen demand we released there. Okay, so let's copy that. And then we go back to acetic acid, economics, and we just add the 11 euros here. So we have the $5.33 plus 11 is, of course, $16.33. So this is our waste disposal cost for acetic acid. Now, we have also in our waste stream sodium acetate. So sodium carbonate, if we would have an excess amount of sodium carbonate, it's not consuming oxygen, it's fully oxidized, so therefore that's not a problem. But sodium acetate, of course, we also have a chemical oxygen demand. So we are not charged for the substance per se, but we're charged for the chemical oxygen demand. So let's first look what is the chemical oxygen demand of sodium acetate. And it's not in the database. So what now? Well, option 1, you're smart. Then you realize, well, the difference between acetic acid and sodium acetate is simply that it's the salt, it's the acetate salt. So if you think what is happening is that the hydrogen from the acetic acid is protonized, it must be protonized, and the electron still is with the acetate. So this means that the COD of sodium acetate will be the same because the sodium ion will not be oxidized. It will be the same as acetic acid. So you could simply put it here. So where do we get the chemical oxygen demand from? Well, what we could do is ask Alexa. Alexa, what is the chemical oxygen demand of sodium acetate? Alexa? Alexa? Oh, I have no Alexa. And you see, it's of no use. Alexa will not give you this value. It simply doesn't know this value. So you have to do it yourself. You have to look it up. However, I heard last time people said, why did we learn something in bioprocess engineering? If you don't know the chemical oxygen demand, of course you can calculate it because you're smart and you're bioengineers. And now I just briefly show you how you can calculate it. So here you could simply not you could simply now transfer the value from acetic acid, but if you don't know the value, I show you now how to calculate it. So let's turn now to the way you can do that. And what we do is we remember what we did in bioprocess engineering. We talked about electron balances. And the chemical oxygen demand is nothing else. That this is a chemical reaction that you oxidize, you fully oxidize your substrate with your oxygen. And you remember we had an equation there. And you remember we had an equation which directly gives us our oxygen demand based on these degrees of reduction. And now the things are simpler because we don't produce a product and we don't produce biomass. So therefore, we just have to look at the substrate and the chemical oxygen demand. So you could use the equation, by the way, we have in the bioprocess engineering script, just setting the stoichiometric coefficient for biomass to 0 and the product to 0, and you will have it. But of course, you also can do the same if you just newly set up the electron balance. Now let's do that. Just that you see that your bioprocess engineering course was worth for something. Here we go. Okay, at the end, the equation, what we're talking about is very simple. It's our acetic acid plus A oxygen gives carbon dioxide plus water. B carbon dioxide plus C water. This is our general equation. So we term that as a substrate, and you remember the general way to put the substrate was this C omega H X O Y. So this is the way we could generally put this equation. And now, if we want to do an electron balance with this equation, so we have no biomass, we have no product here. We completely oxidize this. This is a chemical oxygen demand. We completely oxidize it. Now, what happens? Now we can do that as follows. So now we do the electron balance. So we look at the available electrons, and you remember the available electrons of carbon dioxide and water. Of course, it's water, it's not hydrogen, is 0. So we only need to look at this part here. And you remember, we just need to add up then the available electrons. And the available electrons are within the degree of reduction. So the degree of reduction, remember, for the substrate is the same as available electrons divided by the number of carbons. And in the case, and you remember that carbon has 4 available electrons, so it's W fold 4. Hydrogen has 1 available electron, X fold 1. And oxygen has -2 available electrons, so it's Y fold minus 2 divided by omega. This is our degree of reduction by definition of our substrate. And these values are tabulated, or you can just calculate it. So if we do our electron balance, it means that the electron balance is simply the degree of reduction fold number of carbons. This is the available electrons for our substrate, plus A fold 2 fold minus 2. These are the available electrons for oxygen. Is equal to 0. This is our electron balance. This is the same as we did for the biomass. And if we now solve this equation to A, of course we have then for A, I just solve it, is equal to the number of carbons fold the degree of reduction of the substrate divided by 4. And now just calculate that for acetic acid. Degree of reduction of that acetic acid is, of course, it's equal to, we just put the formula here, just in parentheses. Now we have 2 carbons, so it's 2-fold 4. We have 4 hydrogens plus 4-fold 1. And we have 2 oxygen plus 2-fold minus 2, and we have 2 carbons divided by 2 is equal to, now we just calculate that, so it's 4. The degree of reduction of acetic acid is 4. And now if we just put that in, this we put away, and if we just put that in this equation, then we get A is equal to 2, because we have 2 carbons, fold 4, that's the degree of reduction, divided by 4 is equal to 2. This is mole per mole. And now, of course, we have to convert this into grams per gram. Fold, and then we have now, this is mole oxygen per mole substrate. And then we just multiply this with the molar mass of oxygen. It's 32 grams per mole oxygen. Kick this out. And the molar mass of acetic acid, this we can calculate in our large brains. So we have 2 carbons, so it's 2 times 12. We have 4 hydrogens, it's 4 times 1. And we have 2 oxygens, it's 2 times 16. And if we add all this up, we come to 60 grams per mole. Zack, zack. Now again, we type this into our pockets calculator, and we end up with a calculated value of 1.067 grams per gram. And now what is this value actually, this 1.067 gram per gram? This is exactly the amount of oxygen we need to fully oxidize our substrate. How much gram oxygen do we need to oxidize our substrate, to oxidize 1 gram of our substrate? And this is by definition the chemical oxygen demand. This is the calculated chemical oxygen demand. This is nothing else than our COD. And this is, of course, nothing else than our yield coefficient YOS. So YOS is exactly the same as the chemical oxygen demand. Okay, so you see, this is how so simple it is to calculate the chemical oxygen demand yourself as soon as you remember what you did in bioprocess engineering. Yeah, and with this, you can, with this simple formula, twofold, or the number of carbons for the degree of reduction divided by 4, you can simply calculate the chemical oxygen demand for any substances. You know the structure formula and the degree of reduction, you know the sum formula and the degree of reduction. And then you just need to convert this value, this molar value, with the molar masses, and then you have directly the chemical oxygen demand. It's so simple. And of course, the real chemical oxygen demand is a measured value. But this value must come close to that. It might be a bit lower, but it should come close to that. The biological oxygen demand, of course, that's a different story. Yeah. So we have now the chemical oxygen demand. We have calculated it also for sodium acetate in this case. We have calculated it for acetic acid. So we can put it in. Of course, it's exactly the same value. It's 1.067. So this is our chemical oxygen demand. There will be an output about the pollution, but we need to transfer this value now also in an economic value. And of course, it's the same as before. We're charged per kilogram COD, we are charged $5. So it's again, we have no selling price here, unfortunately. It's again $5 fold 1.067. And of course, it's the same as before. It's then $5.32, which is our waste disposal cost for sodium acetate. In this case, it's just the COD. In the case of acetic acid, it was also the charged price for the substance itself. Okay, so now we're happy. We have now adjusted the demands. Okay, and now we can go and do the economic calculation and look what happens. Okay, here we go. Now again, what we do is we do the mass balance. We do the economic calculation. What we do now is we go to reports and we display the economic report. So let's do it. Reports, reports, and we go to economic evaluation. Here we are. Now it takes a second. And you see that now an economic evaluation report is displayed. And you see this is really cool because you have now, of course, our net present value and so on is zero because we don't generate revenues. We just generate costs. But now we can go down. And you see we have here our equipment. You see our still reactor, $630,000. Now we can have an analysis also of what is really the cost, what is attributed to that. So you see that the equipment purchase cost is not just the price, it's also additional costs. But you see then all these installations and so on brings us up to 2.5 million. Then we have indirect costs and engineering, construction, and so on. So at the end, this is how much our plant costs. This is a lot just for a neutralization operation. Okay, but now labor costs. We just wanted to see the waste disposal costs, yeah, and waste treatment disposal cost. So this is our waste treatment cost, and this is the cost attributed to the sodium acetate product stream. And you see this is the amount which comes out, and this is the cost. So it's $1.6 million disposal cost for this sodium acetate stream. The number you have in the sheet are always a bit different because it readjusts the value. So it's more or less the same. So $1.642 million. I think I put 532 instead 533, then it should be the same. Okay. So you see that's a substantial cost factor, and this is just the aqueous waste, and the values which were inside there are not completely out of range. So you see this is a substantial cost factor. So this is the economic report, but you could also display an environmental impact report, which that doesn't just show you the cost, but it shows you what you do, how you harm your environment. Yeah. And by the way, if you would have done it yourself, I'm quite sure that you would have forgotten to adjust the COD value for sodium acetate. So this is an example where we at the beginning usually neglect all the things we think we don't need. However, in this case, of course, we need the COD, so we need to put it there. It's not a problem if you don't do that at the very beginning, because sometimes you don't foresee all the factors you need. However, you should be aware what you did not yet adjust. Okay, now we look at the environmental impact report. You see that there are many different reports with respect to economics, emission, and so on, which is quite interesting to look at. But here we do the very basis. Again, example 1 is just showing you the basis. So let's go to the environmental impact report. And environmental impact is so important that we start right away and consider that as basis. And you see that this gives us a summary what is the aqueous waste, and you see that this is our waste stream, how much waste we produce there, and you see what is inside of your waste, how much kilogram per year is in your waste, or per batch and per year. And then you see that in this we have our waste subdivided, and if we go to number 5. Then we have the environmental properties, and then you see here we have our COD value appearing, and this is the COD which is produced by waste type. I think in the example paper it's a bit lower. It's because there just the value was copied and we used the calculated value for the COD of sodium acetate, which is a bit higher than the measured value. Okay, so of course the BOD values are not correct because we didn't give a BOD value for the sodium acetate. So be careful here reading these data here. Yeah, so it will be. Of course, you could, for the BOD value, you could use the same ratio BOD-COD. COD is always the higher level. And then because the metabolization of acetate is likely to be similar to acetic acid. Okay, so this is how you can do that and how you can end up with this. Again, of course, this way to do that for a neutralization procedure is not the correct procedure. There are other unit operations which fit to that, which have then pull operations for the sodium, not the sodium acetate. Whether you use then sodium carbonate for neutralization is also another question. But this is in principle, I just want to show you how you can translate that into economics. This is again very simple, but this is to start with. So you now have an idea how to set up a simple process and how to set up economics. And in example 2, then we go for a real bioprocess. We do fermentation. And in example 2, we also will do then separate operations and not just one unit. We will do several procedures in a row. And then, of course, we also need to think of schedule and things like that. Okay, that's it. Thank you very much for your attention. Have fun in trying the things yourself, play around a bit, and see you next time when we talk about example 2. Goodbye.